Okay guys, here's board problem 24. You're going to need board problem 23 to find out which of the following statements are true. Okay, so you're going to have to pull out that board problem. Are all three symmetrical? We talked about that yesterday. That's number one. Number two, the first is skewed to the left while the third is skewed to the right. Number three, the second is skewed on both sides. And then you have your choices there. And take a moment and look at your parallel box plots that we had yesterday, and you can probably pause it right here, and then I'll scroll over. Okay, so the first distribution, the median is far to the right of the box, so that ends up being the first one is skewed to the left. And similarly, in that third distribution, it was skewed to the right. Only the middle distribution looks symmetrical around its median, that middle line in the box right there. And there's no such thing as being skewed on both sides. That's just made up. So typical AP stuff likes to throw in funny things like that. Okay, here we go. Okay, so here's the review for our test on chapter 4, and I believe this will be on Thursday, the test, okay? Uh, Section A, number 1. If a plot is exponential, notice the x is in the exponent of y equals a times b to the x, then log y will be make it linear. Okay, so leave x alone and log y. If the plot follows, your scatter plot follows a power function, y equals a times x to the b, then log both the x and the y, and that'll make it linear. And sometimes you don't know which one's which. You have to use your ratios to see if it's exponential. I'll explain that later. And right here. To help determine whether it's exponential or power function, then you calculate the ratios of the y's. And if they're approximately equal, then it's probably going to be an exponential one. Okay? All right. Sometimes exponential equations won't graph on your calculator, like that one we talked about on the quiz. That's due to the large negative number in the exponent. And so this was the one from that quiz, y equals 10 to the negative 30 power. 30 point something something something. That negative 30 point something makes that 10 power basically 0 in the calculator, because remember, 10 to the negative 30 is 1 over 10 to the positive 30, which is 1 over a really big number, which is basically 0. Okay, so the trick is to put in y sub 2 equal to 10 to the y sub 1 power, and that'll help you graph it and trace it and get prediction values on that. Okay. All right, so typical exponential curves, you guys, in this y equals a times b to the x power, the size of populations of animals as they grow and grow and grow, obviously in the absence of predators or limited resources. Those are typical exponentials. Okay, money investment at a constant rate, like that example I show you, the power of compound interest is, you guys need to start saving money, by the way, right away. Make yourself wealthy when you get older. Average professional sports players, they have grown, their salaries have grown exponentially, particularly baseball players. And that football player who won the Super Bowl, he's got the highest paid salary, by the way, total exponential. Okay, the cost of prescription drugs and any epidemics, like flu epidemics, they tend to be exponential. Okay, if your situation fits these, then x log y or x natural log y, that's what lny means, should straighten it out. We haven't done an lny, but it's the same thing, you guys. You get the same data and stuff. Not the same data, but you get the same r squared and everything and the same predictions and stuff. Okay, but just stick with logs. Okay. All right, typical power curves are like three-dimensional versus one-dimensional, like that fishing thing that I talked about. Like the weight of a fish, which is volume, which is cubic units, and its length is just in units, you guys. So it would be like the weight equals the length cubed, or calculator terms, y equals a times x cubed. Okay. If it's a power function, then log both the x and the y. Okay. Remember, we want to straighten your data out, so you can get a least square regression line, an accurate one where r and r squared are close to 1, and that'll help us predict future events. So does a scatter plot look like a log function or a square root function? And we just briefly talked about this in class. So a log function looks like a square root function, looks like that if it's going to the right like that. If that's the case, and we didn't do one of these in class, but all you would do is log x. and leave y alone, and that'll straighten out the data. So I would take x, and in list 3 I would go log of list 1, because your x is list 1, and then I would do a least square regression line of list 3 comma list 2. Okay, all right. So things like sound intensity, decibel scales, magnitude of earthquakes, the Richter scale, human memory, or human height throughout the years are typical log type functions. And actually, as you get older, you start shrinking, like me. So section E, interpreting correlation and regression. Okay, we understand that both R and your least square regression line can be strongly influenced by a few extreme observations, so sometimes we can delete them. Recognize possible lurking variables that may explain the observed association between variables x and y. Understand that even a strong correlation does not mean that there is a cause and effect relationship between x and y. And I have a classic homework problem in your homework that goes with this when you return. There's one just like this. You get a strong correlation, but there's no relationship. Anyway, relations in categorical data. From a two-way table of counts, find the marginal distributions of both variables by obtaining the rows and sums, the row sums and the column sums. Okay, so you're going to be given a two-way table. Always make a column sum and a row sum on that, and express any distribution in percentages by dividing the category counts by the total counts. Okay, and then describe the relationship between two categorical variables by computing and comparing percentages. You know, like the bar graphs that we did. We can see the comparisons of the different percentages. Okay, often this involves comparing the conditional distributions of one variable from the different categories of the variable. Okay, and lastly, be able to recognize Simpsons Paradox and be able to explain how lurking variables switch the data around, like the example that we had with the hospitals on yesterday's notes, or the first day of school with the airplanes. Those are total Simpsons Paradox. Okay, and I'll see you back in class.